Welcome to qnawire.
Okay, so we know the power output can be equal to m dot times H01 minus H02, which is m dot times Cp times T01 minus T02. M dot here is the mass flow rate for the combustion. H01 is the initial enthalpy for the combustion. H02 is the final enthalpy for the combustion. And we know Cp here is the specific heat for the combustion and the constant pressure. And T01 is the initial stagnation temperature. And T02 is the final stagnation temperature. So therefore, we have W dot R over M dot is equal to Cp times T01 minus T02. And W dot R over M dot here is the term we're looking for to determine, which is the power output of the turbine per unit mass flow. Okay. So while we know the specific heat ratio can be equal to Cp over Cv, and we know Cv is the specific volume, I'm sorry, not specific volume, specific heat at a constant volume. Okay. And the gas constant R can be equal to Cp minus Cv. So therefore, if we do some arrangement here, eventually we'll have Cp is equal to R over 1 minus 1 over K. So therefore, have W dot over M dot is equal to 1 over 1 minus 1 over K times T01 minus T02. And since the process was being assumed to be isentropic, so therefore the relationship between the initial stagnation temperature and the final stagnation temperature can be expressed in red letters here, which is T02 over T01 is equal to P02 over P01 to the power of K minus 1 over K. So eventually you have T02 can be expressed as T01 times P02 over P01 to the power of K minus 1 over K. So we know P02 here is the final stagnation pressure, and P01 is the initial stagnation pressure. So now we can plug in back to the equation. So eventually you have W dot over M dot is equal to R over 1 minus 1 over K times T01, and then multiplied by 1 minus P02 over P01 to the power of K minus 1 over K. So we know the gas constant is 0.287 kilojoule per kilogram times Kelvin, and the specific heat ratio is given as 1.33. We know the initial stagnation temperature is 690 degrees Celsius, which is 973 Kelvin, and the final stagnation pressure is given as 100 kilopascal. The initial stagnation pressure is 0.75 megapascal, which is 750 kilopascal, and the specific heat ratio is 1. Oh, why did I write it again? Interesting. Okay, so that's all we need to determine the power output per unit mass flow rate. So therefore, let's plug in back to the equation to determine the power output of the turbine per unit mass flow. So this can be equal to (0.287 kilojoule per kilogram times Kelvin over 1 minus 1 over 1.33, and then multiplied by 963 Kelvin, and then multiplied by 1 minus 100 kilopascal over 750 kilopascal to the power of 1.33 minus 1 over 1.33. And this will give us the power output per unit mass flow rates is about 438.2 kilowatts. And this is the answer for this question.